Imagine an invisible landscape dominated by a single massive charge. It projects a powerful electrostatic field into the surrounding space, warping the environment. Let's introduce a protagonist, a positive test charge. To push this particle toward the central sphere, an external agent must exert force to overcome the natural repulsion of the field. As the particle moves closer to the center, the field's resistance increases. Moving the charge through this space requires an increasing amount of mechanical effort, which physicists define as work. Work is a variable metric. Consider two particles, one with charge q, the other 10 times that. Pushing the larger particle the same distance requires 10 times the work. Since energy changes based on charge size, work cannot map the field's true intensity. To map the field itself, we need to identify a property that remains constant regardless of which particle we use to measure it. By calculating the work done per unit charge, we strip away the characteristics of the test particle. This isolation reveals a pure characteristic of the electrostatic field. To visualize this, we place a unit positive charge, a particle with a value of exactly 1, at an initial starting point, labeled point R. In this schematic, the unit charge moves towards point P. The outward electric force and inward external force must remain equal. This zero acceleration constraint ensures all effort overcomes the field's repulsion. The work performed is stored as a potential energy difference between these coordinates. This is equation 2.4. It defines the potential difference, Vp minus Vr, as the total work done per unit test charge. At this stage, the measurement describes the energy gap between two locations. We have established a relative difference in space, but we have not yet assigned an absolute value to a single point. We must also consider if the specific route taken between these points changes the energy required. We can test this by moving the charge along 3 different paths: a direct straight line, a wide arc, and a wandering, chaotic route. Regardless of the path, the work done remains identical. This confirms the electrostatic force is conservative. This path independence allows us to define potential as a fixed, completely reliable value for any specific coordinate in the field. While an arbitrary constant could be added to the total potential energy, the physical significance lies in the difference between points, which remains unchanged. The field behaves like a staircase. The height gain between steps is determined by their position, not by how you choose to climb from one to the next. If we can only measure differences between points, we need a way to define the absolute potential of a single location. We require a universal reference point, a sea level where the potential is agreed to be 0. To find this baseline, we travel far beyond the influence of the central charge. We move outward until the electrostatic field is no longer detectable. In this void, an infinite distance away, the field has no power. Physicists set the potential at infinity to 0. Now we observe a unit charge beginning its journey at this infinite reference point and traveling into the field until it reaches point P. Because the starting potential is 0, the total work done during this journey represents the absolute potential energy at point P. This is the resulting formula for the potential, V, at a distance r from a point charge. It provides a specific value for any point. This value acts as the altitude of the field. It tells us the energy state at that exact distance relative to the 0 point at infinity. By defining electrostatic potential as the work required to bring a unit charge from infinity to a point, we create a definitive elevation map for the invisible world of charges.